All right, gentlemen, I'm just still booting things up. Things are still warming up. We'll be getting started in just a minute. Done. Let's see. Okay. Oh, I got my notification that I'm streaming. I finally got that working again. Okay. Let them in. Let's share. Thank you. Screen. Okay. Here. And participants to another group. Gucci. Okay. All right, gentlemen. So let's see. No real announcements. We're just kind of moving forward with where we left off. If you have questions, about anything, feel free to unmute yourself to get my attention, and we can talk about it. Otherwise, we're just going to kind of move forward. Let's see. So last time we began our exploration on chapter 4, the final chapter, right? That we're going to be talking about. It's obviously not the final chapter, but it's the last thing that we kind of need to talk about, that we set our attentions for. And so we kind of summarize integration as the reverse of differentiation, right? So chapters 1, 2, and 3, where we introduce the derivative, explore techniques on finding the derivative, and we explore some applications of the derivative. So then with chapter 4, we're looking at, given the answer, how can we work backwards, right? So, we give an answer, how can we work back to get back to the start, right? Okay. So in section 4.2, we're going to look at antiderivatives as area. So some objectives here: find the area under a graph and use it to solve real world problems. Use rectangles to approximate the area under a graph. Let me see, a vehicle travels at 50 miles per hour for 2 hours. How far has the vehicle traveled? So if we do time versus velocity, notice that his speed is constant, 50 miles per hour, so it's just a steady speed. And then in the first hour, he's traveling at steady speed for 2 hours, right? So with this setup, when we do the speed versus the time, notice the shape that it makes is what, a rectangle, right? And so we're going for 2 hours at 50 miles per hour, then, but the velocity times the time, right? So miles per hour times hours to leave us the distance, right? So 2 hours times 50 miles per hour, if it's a steady speed, they should travel 100 miles, right? But just kind of notice the whole setup. We have our constant, and then if you consider the area under the curve that's created by this shape, it gives us the distance, right? And that's essentially what the integral or the antiderivatives tells us. When we take the integral of these functions, it's basically giving us the area under the curve between the function and the x-axis, right? So that's, in a graphical sense, that's what the integral is telling us. Here. Right? So again, the vehicle travels at 50 miles per hour for 2 hours. How far have they gone? 100 miles, right? We treat the vehicle's velocity as a function. So the velocity is just a steady 50 miles per hour. We graph this function and we sketch a vertical line at x equals 2, and then that'll give us a rectangle, right? This rectangle measures 2 units horizontally, so that's 2 hours, and 50 units vertically, right? So then the area is going to be the distance the vehicle has traveled. So 2 hours times 50 miles per hour, the vehicle goes 100 miles, right? The main takeaway here is that the main thing that the underlying theme that you're going to notice is that the integral is going to give us the area under the curves of our functions, right? That's the main takeaway. keep going. Let's see. So it says the velocity of a moving object is given by this function, where x is the hours and v is miles per hour. Use geometry to find the area under the graph, which is the distance the object has traveled. Okay. During the first 3 hours, so from 0 to 3, and then between the 3rd hour and the 5th hour. Okay, we got this. So it's pretty much the same setup as we saw in the previous example. We're going to graph that function. Let me see. It looks like we're doing velocity versus time again. All right, let me get some paper. Space. This is slide 7. Let's copy and paste. Okay, that should work. Let's see with my battery. I see it here. Yeah, that's good. Okay, guys. All right. All right. I think I'm just gonna do a rough sketch, and that should be okay. Graph paper probably be easier though. Graph paper takes a little bit longer for me to set up, but usually it turns out a lot better. Okay, we're gonna start here. So I know we had a v of x. I think it was just 3x. Okay, or I guess we could say v of t. Let me just look at it instead of trying to do it from the dome. Yeah, v of x is 3x. Okay. So that's our velocity function, and we're gonna plot velocity versus time, right? I think most of our stuff is going to be happening in quadrant 1, so I'm going to put my origin about here. Okay, let's see. I'm just going to go, let's see, I'm going to say like 1, 2, 3, 4, 5. That should be more than enough. Positive x is in this direction. Let's try that again. One more time. Okay. And let's see, for the positive y, I'm thinking like maybe get up to like 15 or 20. Let me see. Can we go 2, 4, 6, 8, 10, 12, 14? Then we're going to work with that. Okay. So positive y is in this direction. What is going on with my graphs today? It will not draw the cursor. There we go. Okay. So here's our positive x. Here's our positive y. The origin, we went by, we said 3 to 5. 1, 2, 3, 4, 5. Let's extend this one just a little bit. Okay. I think we went by ones here. This was like 1, 2, 3, 4, 5, 6, 7. This is like -1, 2, 4, 6, 8, 10, 12. Let me see. 2, 4, 6. Let me move it down just a little bit. What I can do. Nope. I'm not feeling that. Okay, that should be okay. Extend this guy a little bit too. Okay. let's see, 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay, I feel better about that. Okay, and again, these went by 2, 4, 6, 8, 10, 12, 14, 16, 18. Okay. Another thing I like to do, so like this. I don't know, for whatever reason, like creating a graph on grade paper is fine, but then I just feel like graphing it on these dots are like easier for me. I'm just doing it because I can. I'm gonna get the student in the waiting room. Let's see. Right here. Okay. Well, you guys are hanging in there strong. Too bad. I mean, it could be better, but it could be worse. So, we'll go with it. All right. So let's look at the instructions one more time. We kind of been spending most of the time creating a graph. It says use geometry to find the area under the graph, which is the distance the object has traveled for the first. So we want the area when as x goes from 0 to 3, and as x goes from 3 to 5. Okay, so let's graph v of x equals 3x. What is that? That's just a diagonal function. It's just a line that has a slope of 3. So we go what? Up 3 and over 1, and keep plotting points in that fashion. So let me see. If we go up 3 and over 1, there's a point there. Say 1, 2, 3, 1, 2, 1, 2, 3, 1, 2. Right, and it just kind of continues in that fashion. Right. Same thing here. 1, 2, 3, 1, 2. So we should get an image. Lost my place. So let me think. 1, 2, 3. It'll be right there. A little bit off the graph of what I want, but that looks good about there. Let me see. The official one is there. So about there. Okay, yeah, that'll work. That'll work for me. All right, so we get an image like this. This is so now I just got this flash on my mind. I'm totally being like gossipy, but like that Sean Combs stuff was wild, like something out of a movie. And then speaking of movies, I found myself watching. There's like 3 different things on Netflix I was watching nearly simultaneously, not literally. There's this one show called The 3 Body Problem, which was interesting. I was like, yo. So I mean, it's a little bit slow, but it was interesting. I still would recommend check it out. Then after that, I watched this movie called Damsel. I thought that was it had about the same rhythm, but I think it was still worthy of watching. And then finally, I'm watching this show called The Gentleman on Netflix. These are all recommended. I like Friends and stuff. So, just check them out. Just random different topics. One of them kind of does pertain to like this a little bit, but you can always weave things into mathematics. But yeah. Okay. So if this is our graph, this is our graph of v of x. And that was just a random thought that just like shot across my mind when I was trying to create this thing. Okay. So this is our graph. And then we're just going to drop a vertical bar. Let me see. We want it from 0 to 3. So we just want something from here to here. We're going to find that area. Let's go style dash. That's too thick for me. About like that is good. And then we also, for the second part, we wanted to do it from 3 to 5. Copy. I could have just duplicated. I keep forgetting I can duplicate. Okay, right? So we basically get like 2 triangles, right? And then so we can use the formula for, I think I'm done with that image. Let's do this. Okay, nope. Okay. So like, let me see. The area of a triangle, right, is what? 1/2 the base times the height. Okay. And let's focus on this first triangle from 0 to 3. That's decent. There we go. That's what I was trying to get. Style. I like to fill. You know what? Let's actually use this one. I'll get them in just a moment. Style. Ugh, I'll use that one too. Man, I am not getting my clicks today. Style. Let me change this first to like that is fine. Fill. That's decent. I can delete this for now. Let me let the student in. Who else? All right. All right. So let's just do the green triangle first. So area of a triangle is what? 1/2 the base times the height. So if we are doing the green triangle, that's going to be 1/2 it's almost got that I have. So let me see. The base looks like it's 3. And the height, what is that, 9? Uh-huh. 9. So then the area of that triangle, what is that? 9 times 3 is 27 over 2. 13.5 units. Or yeah, whatever the units are, I guess miles. Just check something. Hours, miles per hours, right? So that should be miles, right? So again, we had our velocity function in blue, and then we found the area under the curve as x went from 0 to 3, and so it made a right triangle, right? So we use the area of a triangle is 1/2 the base times the height. Let me see. I need another color. Let's duplicate this guy. Style. Let's choose this color. All right, that's fine. So with the second part, now really what it wanted, let me see, what is it? Blue and yellow. This is fine. Now really what it wants is the orange part, right? It doesn't want from 0 to 5. It wanted the distance traveled from 3 to 5, right? So what we can do is find the area of the larger triangle and say, if we want just that lighter part, not the double layer part, if we want just the orange region here, right, just this region, what we can do is say the larger triangle, find that area minus the area of the smaller triangle, right? And that should leave us the area that we want, right? So let's find the area of the larger one. So the area of that larger triangle, again, 1/2 the base times the height, 1/2. The base looks like it's 5. The height is what, 15? What is that? 50 plus, so that's 75 divided by 2, 30, 37, no, 38, 75. So 70 will be 35, 36, 37. I think it's 37, 37.5, right? I'll give you one. Once I hear another one, I'm gonna turn it off. 37.5 miles. Oh, well, that's the larger triangle. So then we have to say the larger triangle minus the smaller. So then it's because I know that sometimes students kind of change devices. This one. Let's see. So if we say the larger minus, if we say the 37.5 minus the 13, minus the 13.5, I don't know. If there were 20, you can just remove those. So 37 minus 13, 20 will be 17. So plus another 7, 24. Yeah, 24. Looks like it's 24 miles. Okay. So again, the first question asks, how far did they travel? In the first 3 hours, we got 13.5 miles. And again, all we really did was find the area of the green triangle. Kind of want to change the shape. Come on, that's not what I drew. Let's try, let's see if we go like this. Does that work? Okay, I think that worked. So you can do like a polygon tool. I think the other tool may have thought that I was trying to draw a rectangle or a square or something. And then if I go style, stroke is like that is decent. And that's exactly what we want. Right? Okay. All right. So again, if we wanted the distance traveled between the third and fifth hour, we said the larger triangle, the area of the larger triangle minus the area of the smaller triangle. And so we got a distance of 24 miles. So, okay, let's see how do we do. We got 13.5 and 24. Did I get everybody? I think so. How many students? We have 17. Okay. No, I think I did. No, I did one person. I think we're okay. Yeah, I think we're good. Okay, let's keep going. I think in the future I might actually start using Teams. I like Zoom, but I'm not gonna lie, I do like the automatic attendance feature of Teams. That does come in handy. It's just much easier. I don't have to like monitor people coming and going. It'll just tell me. It'll just automatically record it. So I think probably in the fall I start using Teams. I do like it. Okay, let's see how do we do. 13.5 and 24. 13.5 looks good. Got our colors inverted, but that's okay. Did I get 18? Did I do my calculation wrong? 9 times 2. Oh, that's just the base. That's a smaller triangle. And 24 is good, right? So what they did, we did the larger triangle minus the smaller triangle to get to the area. They broke it up, that region, into like 2 simple shapes, into a rectangle and then another triangle, another right triangle. So then they just found the area of those 2 simple shapes and then added those together as well, which is perfectly fine. It's, more than one way to skin a carrot, right? Because we don't want to skin carrots, right? Then that's another set of psychological issues. Unless it's a cultural thing, then that's a little bit different. Anywho, okay, so I think we're good there. I usually leave those as exercise for you all. And so rewind sign. So I like that they, for that last example, they broke the unorthodox shape up into the simple shapes and then found the area, because that actually serves as a great segue into Riemann sums, right? So the last 2 examples, the area function is an antiderivative of the function that generated the graph. Is this always true? Is the formula for the area under the graph of any function the antiderivative of that function? How do we handle what? How do we handle curve? I think it's supposed to say, how do we handle curved graphs for which an area formulas may not be known? I think it's not supposed to be past tense. We investigate the question using geometry in a procedure called Riemann summation. Okay. All right. So we're trying to make a connection. So in those previous examples, the area under the curve did serve as the antiderivative. And the question is, does the area under the curve always give us the antiderivative of our function? All right. So let's see. Let's see how this unfolds. So in the following figure, the closed interval AB is divided into 4 subintervals. each having a width of b minus a over 4. So if you took the whole distance from A to B, divided into 4 equal parts, each part has a distance of b minus a over 4. Okay, that makes sense. And then the height of the rectangle. So now notice with these rectangles, they're using that top left-hand corner. They're using the left corner to generate the height, right? So that first rectangle right here, this first rectangle, they're focused on the upper left-hand corner. Second rectangle, they're using the upper left-hand corner. Upper left-hand corner and upper left-hand corner, right? So for this one, that's what they're doing. The heights of the rectangle are f of x1, f of x2, f of x3, and f of x4, okay? So the area under the region, the area of the region under the curve is approximately the sum of the areas of the 4 rectangles, right? So notice, we have this curve. Man, this is going back to like squaring the curve. But anyway, we have this curve, and if we create rectangles based on the left end point, we kind of short some region here, and then we kind of overshoot this region here. We overshoot a little bit there, and we're short a little bit here. So it's not 100% exact. It's an approximation, right? With the width being done in this fashion, right? With us having 4 subintervals here. Okay, so the area of the region under the curve is approximately the sum of the areas of the 4 rectangles, right? So if we want the area of each rectangle, we're going to say the length times the width. The width is the delta x. It's the same for each rectangle with the varying heights. Okay, so we just basically saying length times width plus length times width, length times width, length times width, right? Now we can denote this sum with summation or sigma notation, which uses the Greek alphabet letter sigma, right? So this is read the sum as I goes from 1 to 4 of f of x sub I times delta x, right? Again, the delta x is the same for each one. And then like you could have x1, x2, x3, x4, right? So you let I be 1. So you would have f of x1 times delta x. Then summation just means plus, you let x be 1, you get an answer. Then you say plus, you let I be 2, you get an answer. Plus, let I be 3, you get an answer. Plus, let I be 4, you get an answer, right? Then you stop. All right, so that's essentially what this notation means. This is read the sum of the product f of xi delta I as I goes from 1 to 4. To recover the original expression, we substitute the numbers 1 through 4 successfully for I in this expression, and we write the plus sign between the results, all right? So we let I be 1, we get an answer, plus when I is 2, you get an answer. You keep going until you get to I is 4, okay? All right, so write the summation notation for this. So they want us to write this in summation notation. What are we doing? It looks like we're adding 2 at each step. So like for instance, like if we're considering our i's, this first expression is going to occur when I is 1. This one is going to occur when I is 2, 3, 4, and 5. So if we consider I, right, what's the pattern? If we have I, what we're saying, 2 times I for each step. So that way when I is 1, we get 2. When I is 2, we get 4. When I is 3, we get 6. When I is 4, we get 8, right? So on and so on. So then we want to take the sum. We want to sum these guys up as I goes from 1 to 5, right? When I is 1, we get 2 plus. When I is 2, we get 4 plus, so on and so on. I think this works, right? Again, if anything is not clear, feel free to unmute yourself to get my attention and we can talk about it. Otherwise, I'm going to power on. Okay, hopefully that makes sense. Copy. Okay. So we had the sum as I goes from 1 to 5 with 2I. The sum as I goes from 1 to 5 with 2I. Okay. I'm going to leave this as an exercise. Write summation notation for this guy. So with each expression, they all have the same delta x, but I think we saw this one already, right? So it shouldn't be too terribly bad. So each expression is taken on the form g of x sub I delta x. And we're taking the sum as I goes from what, 1 to 19? Okay. All right. Let's keep going. We're actually almost done with this section. Express this summation without using summation notation. Okay. So first, when I is 1, we're going to get 3 to the power of 1. We get an answer. Plus, let I be 2. We get this. Plus, when I is 3. Plus, when I is 4. Okay. 3 plus 9 plus 27 plus 81. Let's see. Those together bring it to 90. 90 plus 30, is that 120? Okay. Express this without using summation notation. Okay. So let's do this. Let me think. Okay. So we're starting with the sum as I goes from 1 to 30 of h of xi delta x, right? We want to express this without using summation notation. So we're going to write the first few. When I is 1, h of x sub 1 delta x plus h of x sub 2 delta x. And you continue the pattern until you get to h of x sub 30. I'm out of space. Delta x, right? Just shrink it down just a little bit. Just a little bit. Reposition this guy and resize it back. It's decent about like that. Right, so, obviously we're not going to write out all 30. So we just write the first few, like 2 or 3 of the sequence. And then we can use ellipses. That mean the ellipses just mean continue the pattern and then stop when you get to 30. Right, and that's just suffice for this one. Mm-hmm. Okay, so consider the graph of this guy over the interval from 0 to 600. Approximate the area by dividing the interval into 6 subintervals, and then approximate the area by dividing the interval into 12 subintervals. Okay. So we're going to need some space. What slide is this? 27. Copy. Paste. Okay. Working with f of x equals 600x minus x squared. Zero to 600. First, we want 6 subintervals. Okay. So if they want 6 subintervals, we want to take the distance from 0 to 600, and I think just divide it by 6, right? So we're going to say 600 minus 0 divided by 6. So then each delta x for part A, I think earlier we said b minus a over the number of subintervals. I'm just going to call it n. So in this case, that's going to be 600 minus 0, and we want 6 subintervals. So then each delta x needs to have a width of 100 units, right? Okay, so I think graphic is a good idea here. Space. Okay, we'll start about here, I guess. Okay. Let's see. Okay, so this graph. Now, we can choose several values of x. We can just basically plot points. The highest power is the degree 2, so it should be a parabola, right? It's a U-shaped curve. It has a negative leading coefficient, so it should open first. I can make just a moment. Close. Settings. I think we got everybody. Turn this off. This. Let's see. So we have 2 exams and a final. Our next exam is going to occur once we get to the end of chapter 4. So if this is I think this is week 10. I think the exam is like during week 13, something like that. It's a few weeks out. It's once we get to the end of chapter 4, then exam 2 is going to cover chapter 3 and chapter 4. And then the final is going to be from the beginning to the end, right? But again, one thing with the mathematics exam kind of by default cumulative, because we're basically building on stuff we've been talking about the whole while. And so if I ask anything from like chapters 3 or 4, that's based on everything from chapters 1 and 2. So really, if I only ask things from the end, it's going to use things from the beginning, right? So by default, mathematics exams are cumulative. But yeah, exam 2 should cover chapters 3 and 4. That'll be in a couple of weeks once we get to the end of chapter 4. And then the final is a couple of weeks after that. It's going to be cumulative. Let me see. So again, we could just plot points, choose several values of x, find the corresponding y. Oh, actually, I think we're already going to have them because and this is supposed to be our delta x here. Right, each change in x, so each subinterval is going to have a width of 100. So it's going to go 100, 200, 300, 400, 500, 600. It's going to be a total of 6 tick marks. So we can honestly, we could use those, to be honest, yeah, to create our curve. Matter of fact, we can go a little bit smaller. But basically, again, it's a U-shaped curve that opens downward. Then we have some other manipulations going on. But the simplest thing is just choose several values of x, find the corresponding y. But it looks like we're going to be working in quadrant 1. So I'm going to put my origin about like here. And I'm just going to go ahead and start with the 12 subintervals. I mean, you'll see it. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is my positive x in this direction. Okay. My positive x. Now the y's, let me see. When x is 0, we're at 0. If we did negative b over 2a, now I'm just using like, we can use some calculus to like jump straight to like the vertex. Like honestly, from college algebra, the vertex form is negative b over 2a. So we would say negative 600 divided by negative 2. So it seems like the vertex occurs when x is 300. So let me see, 1, 2, 3. Okay. So when x is 300, right? Let me see. That's going to be a 9. That's 18. It looks like it's 1800 minus 900 to give us 900, right? So it looks like we just need to go up to about have like 10 tick marks or about 1,000 going up, right? Let me see. 1, 2, 3, 4, 5, 6. So we can do those by 2s, right? Do something like the following. So let's see, here's our origin. Now these, I did the following. I said this was like 100, 200, 300, 400, 500, and 600, right? And then this would be like negative 50 over here. These, I think, we can go by twos. What's the function at play here? It's just a function, right? 1,000, so 200. So I think we can go like 200, 400, 600, 800, 1,000, and then 1,200. This is our positive y in this direction, okay? So I think this is a proper window. Yep, that's not what we want. We want this guy. Okay. And I think I'm just going to plot some points. I'm going to choose several values of x, find the corresponding y. Let's see. I think I'm going to shrink this down just a little bit and put a table up here. I think that's the best way to go about this one. All right. So we'll do our x versus our f of x. And let me think. Okay. What I'll do just to make it a little bit faster, I'm going to use my calculator. I guess this is fine. Use my other one, but that's okay. The calculator's here. And let me finish up my attendance. So we are missing some gentlemen. Mark is absent. Okay. No surface. All right. Reload. Come on. And refresh. Okay. All right. So what I'm going to do, I'm going to go to my y equals. We got 600x minus x squared. Okay. So then what I'm going to do, I'm just going to look at the table. Instead of crunching all these numbers, I'm going to just make a table that'll spit it out for me. We can have the table start at 0, and we can have it change. I want it to change by 50. Okay. So then I'm just going to hop over to the table. Is that right? 2,700. Wait a minute. Maybe I did my scale wrong. Let me think about it again. If we did 300, I guess it is 18. That's an 18. It's 180,000. 90,000. So I think we need to tack a 0 onto our y values. All right. I think we just need to tack a 0 onto all of these guys. Didn't get it. Let's see. Let's try this. Okay. 12,000. If we go to 300 or 90, maybe tack on 2 zeros. One, two, so 20,000, 2, 40, 60. Is that right? I think that probably is right. I'm sure I was moving fast. So again, we have our table generated here already. And then, I don't feel, I was going to write out the table. I think I'm going to just screenshot that and I'll just use that or something. I just don't feel like writing all that out. But you know how to generate that, right? So then let's just plot these points to get a nice curve. So the first one is the origin. Let me see something. I'd like to, can I just grab that? Duplicate. That looks pretty decent. Cuts. Oh no. Undo. Cuts. Paste. Cuts. And paste. Okay, there we go. All right, let's go back here. So then we have 50, 27,500. So 27, if that's 30, that's about here. Okay. I guess maybe just duplicate. So then the next one is 150. So 150,000 should be here. 150, 67,500. Paste. So if this is 70, 67,500 should be about here. And then the next 280, 80 is here. Okay. Paste. 250, 87,500. So that's here. 390. Okay. Come on. No. Paste. 390 is here. Okay. And then I think it just repeats going down, right? Let me see. So the next one should be 87,500 and then 80. All right. Let me see. Maybe I can just duplicate these guys. If I can duplicate it, if I can flip it horizontally, that's all I really needed to do. Let's see. I don't know if that's an option though. Let's see, duplicate. Let's see if there's a way to do it. Style, group, convert. What if I do this? I can rotate it. I just don't see a way to flip it. Nope. It's getting trippy. Nope, that's not working either. Okay. So I'll just position these because I know it's like using symmetry. So 350 should match like there. Okay, that's not gonna work. What if I get smaller? Okay. 350, 400 should be there. Come on. All right, I'm just gonna get rid of those guys. Thought I could just grab them, but it's picking up the whole thing. Paste, okay. So then 450 should be like here. Nope, it's here. Okay, let's go on to the next one. 500 is here. Paste. 550, the next one is here. And I'm just using symmetry at this point. I would have, if it would allow me to flip horizontally, then we could have got it in one go. 600 should be back to 0. Let's see. That's 360,000. Yeah, same thing. Okay. All right. So then this is our graph that we got. Finally, we get an image like this. Now I think what I can do. That's decent. And I'm just gonna move these points because these are kind of approximations anyway. That's fine. But like that, that's okay. I think it's okay. Okay. All right, so we got something about like that, right? Let's do these as well. Okay. Should be okay. Let's go with it. All right. And actually, what's the time? Okay, I think we got time. Let's keep going. So now this is our graph of the 600x. That's our graph of f of x, basically. So this is our f of x in blue. We'll do our Riemann sums in orange. So if we break it up into 6 subinterval, each triangle should have a width of 100. Now, we can match the way the book did it earlier and use the left-hand corner, right? So like for instance, we're gonna have a subinterval here. Let's just duplicate this. Then the next one is when x is 200, all right, duplicate. And then when x is 300, duplicate. And then when x is 400, is that good? Okay, duplicate. And then when x is 500, okay, we want 6 subintervals. Okay, that's fine. 1, 2, 3, 4, 5, 6. Okay. So if we use the left endpoint, right? That first rectangle has a height of 0, but then we can create a rectangle here. Right? So let's duplicate. We can create a rectangle here. Duplicate. We can create one here where this kind of extends a bit. Duplicate. We can create one here. Again, this is based on the left endpoints. Duplicate. We can create one here. I think we need to duplicate this as well. And let me see. So the first one pretty much doesn't have a height, but that's 1, 2, 3, 4, 5. So we got our 6 subintervals, okay? And let me see. Approximate the area by dividing it into the 6 subintervals. So then, and let's get rid of this. Okay. So then, like for instance, if we think about that first rectangle, if we say the length times the width, right? So the width of all of these guys are 100. The first height is 0, so we're going to say 0 times 100 plus. The next height, when x is 100, so when x was 100, we're at 50,000. And so the height is 50, the width is still 100. So they should all have a width of 100. So then the next one, when x was 200, we're at 80,000. Again, it has a width of 100. Let me see. So that was, let me see, 0, 1, 2. So then when x was 3, I think we were at 90,000. And it still has a width of 100 plus, and then I think it should use symmetry at that point. So if that's 3, the next one is 4, should be 80. Yeah, it is. All right. So 80,000 times 100. And then it should be, let me see, 1, 2, 3, 4, 5. I think the last one is the 50. Handwriting has gotten so much better. I'm pretty sure this is still chicken scratch, but I'm telling you, the way I used to write, even doctors couldn't read it. You know, doctors be having like chicken scratch. All right. Okay. So then we basically add up all those results, and that'll give us an approximation for the area under the curve with 6 subintervals. Right. Okay. I am tempted to use Siri. I'm a little bit lazy. Let me do this instead. Quick, clear. So I'm going to factor out the 100. I'm going to say 0 plus 50, 1, 2, 3, plus 80, 1, 2, 3, plus 90, 1, 2, 3, plus 80 and 50. 80, 1, 2, 3, plus 50, 1, 2, 3, times 100. All right, because if you distribute 100, you'll get what we just wrote. Okay, so then using Riemann sums, if we break the region from 0 to 600 up into 6 subintervals, based on this image, we get an area of 1, 2, 3, 35 million. I feel like my numbers are off. Okay. Can we paste? No, forget it. Okay. Style. I'm gonna go like this. Let me see the time. We are doing pretty good on time. I'm about to wrap it up. So that's the area that we get when we did 6 subintervals. Now let's do this real quick. I think we can do it quickly. I think we can get it in time. I want to duplicate this slide. Okay. So now we're gonna keep what we had before, but instead of 6 subintervals, we want to change n. I'll do the changes in purple. We want to change n from 6 to 12. We want to change that to 12. So it should be 50, right? Siri, what's 600 divided by 12?
600 divided by 12 is 50.
Okay, that's why I did 50 initially. So that way I can use my same graph, right? Okay. So what I'm going to do, I'm going to capture as many of these as I can. Style, I'm going to change them to purple. This also needs to be purple. Actually, let me get rid of those guys. Get rid of these. Change this to purple. Okay. And so now we're going to do it based on the fifth. The width of each X is 50. So we're going to go from here to here. Okay, let's delete that real quick, like that, and it should snap back to the grid. Okay, looking good. Trying to get you guys out of here. I'm watching. I can see the clock. Just trying to get you out of here. Okay, that's good. Let's duplicate. It's a little bit off, but it's okay. We're going here. So these 50s are a little bit more challenging. But we're basically going to do the construction similar to how we did the other part. Okay. So I can make a rectangle here. I'll just duplicate that. I can make one here, duplicate 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 here, duplicate. Come on, just trying to get this gentleman out of here. Duplicate here, duplicate here, and so then let's adjust all these other varying heights. So that one needs to go like there, looks good. This one needs to go up there. It's a little bit off, but we're just gonna go with it. This one goes here. This one goes here. This one goes here. And this one goes here. Okay. So basically we base the height of these rectangles on, again, the left-hand corner. Now I will say that going forward, we'll see that you can base the height of these rectangles on the left corner. You can actually base it on the center, and you can base it on the right, and it all give you the same approximation. Okay. So now I want to say the results that we had before persist. Let me think. Okay. So this. And let me see, if I factor, basically we can change the 100 to 50. So I'm just going to go to make that change. All right, all those 100s become 50. And these results are still there, right? So this was times 50 times. I'm just trying to capture the new stuff, right? So that's a 50, that's 50, that's 50, that's 50, that's 50. Now the new stuff, let me see, we got it when X was 0, we got the hundreds, so then we would need like all the 50s, right? The 50, 150, 250, all those results. So what I'll do, I'm just gonna try to write it shorthand as best I can. Like when X is 50, if we look at our table, okay, let's go to table set. Let's have the table start at 0 and change by 50. Okay. So 27,500. So we're going to shorthand it. 27,500 plus 67,500. Let me see. Yeah. 67,500. Let me see. We did 50, 150. Let's do 250. 87,500. Get rid of this. 87,500 plus. Let me see. That was 50, 150, 250. So then does 350, is that also 87,500? It's 87 and then 67. I think it kind of repeats, right? So then, let me see, 350 was 87,500. 450 was 67,500. That's 450. And then 550 should be 27,500. So we get a result there. We're going to say that times what, 50? Because the width of each one is 50, right? So this is how we can use what we had before. Before, we changed all the 100s to 50. Then we're tacking on these additional points times 50 as well, right? That should get it. Let's see. Okay. So what we can do is take our answer. I think we can just divide it by 2. I'm just going to divide it by 2. We get this. So that way it's like multiplying by 50. Then we're going to say that number plus 27,500. Okay, here, let's do this. Because these are all double. So 67,500 plus 87,500, okay? I'm going to say times 100, right? Because it's 50 times 2, because I only did each one once. So we're going to say times 100, okay? All right, I think that looks right? So then after doing all of that and putting all that together, now we're not going to be doing it like this all the time, but this is just similar to how we had the whole difference quotient definition. This is just like for introduction. We have techniques for doing this quickly, right? This is just kind of drive home a point. 35,750,000, right? So long story short, what you should notice is that I think initially we had 35 million, and then when we did more subintervals, we got a better approximation, right? It's less of these little gaps, right? It's getting closer and closer to the curve. So the more subintervals that we take, the better our approximation is going to be. That was the whole moral of the story there, right? All right, let me see. 0, yeah, they used the left. Let's see. 35 million was correct for part A. That's fine. Come on. Oh, was that it? There it is. And then 35,750,000 was correct for part B, right? So that actually brings us to the end. Where is my slide? No, it's not. Why won't it go? This is weird, right? Okay, there we go. So, you know, 37,750,000, right? Okay. So again, the main takeaway with that last example was that the more subintervals we do, the better our approximation. So then in the future sections, in the next couple of sections, we're gonna push it to the limit, right? You know, we took one subinterval, then we cut that subinterval in half so we can do more. Now we're gonna see, well, how far can we push it, right? Using limits and things of that nature, right? Okay, so that was fun. We're gonna go ahead. Are there any burning questions before we go our separate ways? Share. Let me make a copy of this available for you all. Come on. This is this. I don't know why I'm always scribbling that one. Traditional calculus notes updated daily. We'll go here. Yeah, 4.2. Okay. So when this bar finishes loading, you'll receive a copy of anything that you saw me writing. And if there aren't any burning questions, we're going to go ahead and end the session here. And from one beautiful mind to another, enjoy the rest of enjoy your weekend, gentlemen. Yeah, we're at the end of the week. And so next week, I think from here on out, we're pretty much doing one section a day, right? So Monday we'll do 4.3, and then Wednesday is 4.4. And again, one of the students asked, when's the next exam? So when we finish out chapter 4 with integration, you know, you can expect exam 2, okay? And again, if there are any burning questions, we're going to go ahead and end the session here. From one beautiful mind to another, have a great weekend, gentlemen. I'll see you next week, same time, same place. Take care. Peace. And that was an adventure. We barely got it in there. All right, gentlemen.